So let's delve inside that a little bit more. If we think about prolonged exercise, then, and it's low intensity, then quite clearly there's a net release of lactate. And in fact, one of the things we start to understand, if we maintain that same exercise intensity, that starts to decrease over time. It starts to decrease partly because we overcome an oxygen deficit at the onset of exercise, so supply of oxygen meets demand. But also don't forget that you've got these inactive sites. Not all muscle fibers are going to be engaged. So in this example here where you've got rowers, although they look like they're working maximally in this example, they could be out rowing very low intensity exercise. Now, not all the muscles will be engaged. Although they're doing whole body exercise, there will be some fibers that are not being used for this process. They can become sites which allow for lactate to disappear. The great example is something like cycling. If we've got cycling-based exercise, the predominant areas for lactate production will be in the legs. The predominant site for lactate removal and disappearance would be in the arms or the upper body, because they're less active. They're not completely inactive, certainly the torso is not inactive, but they become sites where you can get lactate disappearance. But as the intensity goes up in cycling-based exercise, you can't suddenly increase the number of inactive fibers, because in essence you can't suddenly increase that fiber number. In fact, it's more likely to decrease because perhaps now the participant pulls harder on the bars, or they start to sway on the bike or whatever. We'd hope they don't, but they may do. So in other words, you get a decrease in inactive sites, and hence this imbalance starts to occur between appearance and disappearance of lactate. So what Brooks refers to is under submaximal conditions, you get a balance between lactate release and lactate uptake, release and disappearance. Hence the lactate concentration, the blood lactate concentration remains fairly constant, because the rate at which the lactate is released, and remember the whole point is that lactate has to be released from the cell. Has to be released from the cell. Remember what lactate is. It's the byproduct of glycolysis. It's not a waste product, but it's the byproduct of glycolysis. So we need to get the lactate. Remember, it contains hydrogen ions, and the hydrogen ions are the part that can cause fatigue. So the fact that the hydrogen ions are attaching to pyruvate is going to reduce the risk of fatigue. It's when hydrogen ions start to back up and they can't attach to pyruvate, or we have excess hydrogen ions, that fatigue may start to ensue. But under low intensity conditions, the balance is struck between the rate of appearance and the rate of disappearance for lactate. Hence the blood lactate concentration remains fairly level. And so what we're dealing with here is lactate consumption. Lactate disappearance is dependent or is related to inactive muscle fibers. And that's a really fundamental part. Don't think that just because somebody's running or somebody's rowing that all muscle fibers will be engaged. That would be crazy, right? Because if they're all engaged, how could you get an increase in force production? Yes, you may be able to produce more force per fiber, but quite clearly if all the fibers are engaged, there is not a real big scope for force development. So we understand that there is this hierarchy of response for fiber recruitment. So in the low intensity conditions, there'll be a large bunch of inactive fibers that can, in essence, consume the lactate and will convert the lactate back to pyruvate. And they will also then, because they're inactive, be able to shuttle the hydrogen ions that were attached to the pyruvate forming the lactate down the electron transport chain to produce ATP. The pyruvate is then shuttled backwards. Remember that glycolysis is a reversible process to produce glucose and or glycogen. Now, the glycogen can either remain in those muscle fibers, because it may be that those muscle fibers become engaged subsequently during the exercise, or it can be released from the cell in the form of glucose and actively transported to the more active fibers to then go into the process of glycolysis to produce ATP. So the lactate, you see why lactate is so important to our understanding, that it is telling so much more about what is going on in terms of substrate metabolism. So again, a schematic showing us the rate of appearance and disappearance, and just because we want to hammer this message home. So here, exercise intensity is being represented slightly differently. It's being represented in terms of VO2, the volume of oxygen. but we understand that VO2 has a linear-like response to exercise intensity. But you can see that we've got the change in the blood lactate response to exercise pre and post a period of training. Now what you can see is pre-training. If you look at pre-training, look at the response. So for given VO2, there's a higher lactate concentration, but also notice that the point of where we get that sudden kick, the sudden turn point, it's fairly hard to discern, but one would argue it's probably in the region of about 1.5 litres per minute, so at about 4 millimoles. But look at post-training. If you go to now 1.5 litres per minute, the lactate concentration has fallen from 4 to about 1 millimole, and in fact that turning point is more closely probably associated with 1.752 litres per minute, and has dropped from about 6 millimoles to just over 2 millimoles. So this tells us something really fundamental about the lactate response. Lactate responses change according to doing exercise and training, and we understand that endurance exercise particularly is fundamental in shifting the blood lactate concentration to exercise. What we see is this twofold response, that for the same relative exercise intensity, in this case represented as VO2, you get a reduction in the blood lactate concentration. We'll come to why in a moment. And secondly, you get a rightward shift in the lactate curve. In other words, the point of transition from predominantly aerobic to anaerobic metabolism, lactate turn point, the kick, will shift to a higher exercise intensity. And so this is a manifestation of, for example, we know that endurance training increases mitochondrial density, capillary density. It increases the availability of aerobic enzymes. All of these are fundamental. But let's take all those as a package. All of those as a package produce the blood lactate response to exercise that you see here. But remember that the blood lactate response to exercise is a function of the rate of appearance and disappearance. So now you start to think, well, hold on, what is it that we're seeing? Well, the key thing to bear in mind is that the number of inactive fibers is unlikely to increase. Unlikely with training to increase. What's changing is the rate of appearance. There will be a slight change in the rate of disappearance because you'll have a greater transport mechanism that we'll look at later on. But on the whole, the predominant response is the rate of appearance. There is less lactate being produced for any given workload. And of that lactate that's being produced, that balance, particularly at submaximal exercise intensities, is met by the rate of disappearance. The net result is your blood lactate concentration measured in a capillary sample decreases. The other factor is that shift in terms of the lactate turn point. So in other words, because we've got a greater propensity for producing less lactate per workload, but we've now got the same number, if not slight increase in availability for disappearance, more inactive fibers, or the same number of inactive fibers, but because we're producing less lactate, those fibers, that proportion of those fibers that become engaged becomes less. Because you're producing less lactate, there's less lactate having to disappear. So the net result is that balance between appearance and disappearance is maintained for longer before the rate of appearance exceeds the available sites for the rate of disappearance, and we get to the turn point. So the net result is you get a decrease in the blood lactate concentration in terms of the absolute concentration, and you get an increase in the exercise intensity associated with the lactate turn point. And so this is really important to us. This really drills down to why we see these blood lactate responses, because it's very much about the balance between appearance and disappearance. And again, just to really put this into perspective, so this is from the same study, and again you've got exercise intensity in terms of VO2, but now can you see exactly what I was referring to, that Panel A is appearance and panel B is disappearance. So A is on the left, B is on the right. And you can see that the rate of appearance pre to post decreases. So there's less lactate appearing because less lactate is being produced because you've got greater aerobic machinery. So there's more mitochondria. If you've got more mitochondria, you've got greater sites for aerobic metabolism. If you've got more capillaries, then you've got a greater network for getting oxygen to the cell and also getting CO2 away from the cell. If you've got more mitochondria, we tend to find we've got greater aerobic enzyme activity. So in other words, the process of things like the TCA cycle can work more efficiently. So appearance decreases. We also notice that there is a slight decrease here in the rate of disappearance. Slight. Okay, it's certainly not significant, but the key point is that the rate of appearance has decreased. The rate of disappearance is pretty much following that same response pattern. There's not a massive change in the available sites for disappearance, but those sites that you have got are more efficient at taking up the lactate. So the net result is what we saw on the previous panel, which is the blood lactate concentration is lower for any given exercise intensity. Just to go one stage further, this is some data from Jens Bangsbo group published in the Journal of Physiology. Don't necessarily worry about what it is that you're getting at, but the key point is that it's showing you here the blood lactate concentration, blood lactate, in arteries and veins. Now remember, arterial side is oxygenated, venous side is deoxygenated. And quite clearly, what you can see, okay, that the squares are arterial and the triangles are venous. But for any given zone, so they're doing different activities in L1, L2 to L2 plus A and L3. They're different zones, they're different exercise intensity periods. But you can see as the intensity of exercise goes up, can you see that there is an increase in lactate because you can see the venous concentration. Now the venous concentration for any given area, it doesn't matter what N and H are, but they're in essence two conditions. But the venous concentration is higher than the arterial concentration. Makes sense, right? Because the lactate is produced at the cell, it comes out on the venous side, and it's through the venous circulation that lactate is now going to be transported to the inactive fibres. You would not expect to see the lactate concentration high on the arterial side. Okay, you wouldn't expect to see it high on the arterial side. So the net result is that what we see is higher lactate concentrations on the venous side than we do on the arterial side, because it's the venous circulation that is used in terms of the movement of the blood lactate. And again, here we've got the idea of appearance and disappearance, and here you've got just lactate release. So you can see that lactate release across this period of time, again, under the two conditions. We've got normal conditions, and then we've got hypoxic conditions. So hypoxia is where we've got a reduction in O2 availability. So quite clearly, if O2 availability is released, lactate production goes up. So the release of lactate will be far higher under hypoxic conditions than it will be under normal conditions. So H, which is the black circles, is hypoxic. N, which is normal conditions, is a normal ambient condition. Don't worry so much about what the conditions are in terms of L1, L2 plus A and L3, but just look under L1 just as an example. If O2 is limiting, the net result is under hypoxic conditions you get a massive increase in substrate level glycolysis, so the amount of lactate being produced, what we record in the circulation, goes up because more lactate is being released from the cell. It doesn't tell us about disappearance, but more is being released from the cell. Here we are getting down to some data again in MedSci Sport and Exercise, which quantifies the uptake and release in relation to fiber type. Okay, fibre type. So you can see above the dashed line is uptake and below the dashed line is release. And what they've done is they've just summarised the fibre types in terms of glycolytic, which we'd refer to perhaps as more type 2B, mixed, which is type 2A, and ox, which is more slow twitch fibres. And so what they're suggesting is that when you have a blood lactate concentration of, say, let's say 1 millimole, which is very low intensity exercise, that the release is almost predominant. There's very little uptake under those conditions. As the concentration rises, the majority of the lactate is being released, not surprisingly, from the faster twitch fibres, because they're the ones that produce more lactate than the slow twitch fibres, but the majority of the lactate is being taken up by the oxidative fibres. You can see that. So the triangle sits above that dashed line. But as you go further up the curve, you start to find that the uptake becomes across all the fibres. But notice that what you start to see is that the glycolytic fibres become almost incapable for any given lactate concentration of taking up the lactate, because they don't have the machinery, they don't have the capacity to take up the lactate. Secondly, they are going to be quite actively engaged at these higher lactate concentrations. They don't have high capillary densities, they don't have high mitochondrial densities or aerobic enzyme concentrations, so they're less capable. The slow twitch fibres are pretty capable at it, but so are also the mixed fibres. They seem to be very capable at taking up the lactate, so the uptake increases in the slow twitch and the mixed fibre population groups. So we can see that the release and disappearance of lactate is very much muscle fibre type specific. And this is some really nice data from Bruce Gladden's group in the American Journal of Physiology. And you've got your plasma lactate concentration on your x-axis, but now what they're just showing is the net lactate uptake. So they're just showing disappearance, just a different way of describing it, disappearance. And what they've got is this at different metabolic rates. So different metabolic rates. And what they've done is they have perfused the dog muscle with different lactate concentrations. And the dashed line is where they've got a metabolic rate of the equivalent of 100 mils per kilogram per minute. So remember, in the dog, it can have a much higher VO2 response. But notice that the uptake, the net lactate uptake, is far greater under exercising conditions than it is under resting conditions of 3 milliliters per kilogram per minute. So despite the fact that the plasma concentration that they infuse goes up, the uptake doesn't increase. In other words, this tells us something fundamental, that in order to promote lactate uptake, there has to be a raised metabolic rate. So in other words, you have to have an increase in O2 delivery to the muscle. There has to be an increase in oxidative phosphorylation at the cell. There has to be an increase in the enzymatic activities. There has to be an increase in both oxygenated and deoxygenated blood flow. In other words, you don't get high uptake, even if you've got high lactate concentrations, which is not an unusual thing in the human. Even if you've got high lactate concentrations, you don't get the uptake until you raise the metabolic rate. So the raising of the metabolic rate, although one argues that it's the raising of the metabolic rate that drives the actual lactate production, it also is facilitating the uptake of lactate. So although it increases the amount we produce, it also facilitates the amount that we can disappear. So as the metabolism increases, it promotes the redistribution of blood flow, and it also means that in those inactive fibres, their metabolic rate will be raised. They are therefore more capable of taking lactate out of the circulation. Now, this is quite nice in terms of just drilling down a little bit. This is a study published in the Journal of Physiology by Joule. But what it's got is exercise time on the x-axis And then what they've done is they're showing the idea of lactate release and lactate uptake. And so release is below 0, uptake is above the 0 line, but they've got it in the arms and the legs, and they're explaining to you what they're doing in terms of continuous exercise. So they've got continuous arm plus leg, then just arm, then again arm plus leg. And what you can see is that they're doing the kind of exercise which is what's called working on an elliptical trainer. So you're cycling and you're doing the arm exercise at the same time. So now what you can see is that when they're doing continuous arm plus leg, so they're not ramping it up, it's just continuous exercise time, notice that there is a fairly good balance between the release from the arm and the uptake. So can you see the balance between the two? So although we're doing predominantly arm plus leg, the uptake actually is higher in the leg than it is in terms of the release from the arm. In other words, we're producing from the arm, but we're taking up in the leg. Now this is fundamental. Why is this the case? Well, the leg is a greater muscle mass, so there'll be proportionally more fibres available that are inactive to take up the lactate in the legs than there will be in the arms. So it's not that there isn't uptake. It's not that there isn't uptake in the leg. It's just that they're showing you proportionally how much has been taken up in the leg. There will still be, as I say, lactate produced in the leg and in the arm. There'll be lactate taken up in the leg and the arm. But they're just showing you that as the intensity goes up, that you're getting a lactate release. In this example, you can see the arm producing the lactate, but look at the pretty equal balance in terms of the amount that's being taken up in the leg, proportionally more muscle fibres. Now, when they go to just arm exercise only, now, because the legs are truly inactive, look at that, there's a massive increase in the uptake of lactate because you've got these inactive fibres. And then they go to a short period at the end where you've got arm and leg, and what you find is, because they've actually brought the intensity down quite low here, that actually predominantly there's very little lactate being produced, and in fact what they're doing is the legs and the arms are acting under low intensity conditions as sources for the removal or disappearance of lactate. But that middle part is really important to us, that arm section. The arms are the active muscles in this example. They are where lactate is appearing, where it's appearing. The legs are inactive. So the legs, where you've got quite a large muscle mass, are now able to take up the lactate that's been produced, that's been released into the circulation, and convert it either back into pyruvate, into the TCA cycle, the hydrogen isotope electron transport chain, or convert it back to glucose. So if we were plotting the lactate concentration, one would argue that the lactate concentration is actually pretty stable under those conditions. In fact, one would argue that the lactate concentration has probably fallen. The blood lactate concentration has fallen because the net lactate uptake is actually greater than the net lactate release. It's greater than net lactate release. But notice that for the same relative exercise intensity as we have for continuous arm plus leg exercise, that the amount being released is far greater, because they're doing the same relative exercise intensity but with less muscle mass than they had when they did the arms plus the legs. So the lactate concentration goes up, but because they've got the legs not being engaged, they've now got a greater muscle mass that's inactive that can be used to take up the lactate out of the circulation. And this lends itself to a little bit of interesting thought, which is the idea of doing active recovery. It's a sidestep a little bit from what we need to be thinking about, but it does lend this idea that if you are doing, for example, upper body exercise, as an example, let's say you're doing sprint kayak. Okay, so sprint kayak is predominantly upper body. Then it would suggest that actually the most appropriate recovery to do is not to do a cool down on the arms, but actually to do a cool down on the legs. because then you would actually facilitate the recovery process far greater, because remember the arms were the active fibres, so those active fibres will not be so good at taking the lactate up in recovery. The inactive fibres would have been in the lower body, in the leg. They're therefore less fatigued or have been less engaged, therefore they have a greater propensity for taking up the lactate and reducing the blood lactate concentration. Same would be for something like cycling, that if you've done cycling, and of course it's on the legs, that actually it may well be that the best recovery to do is to cycle and then do the recovery on the arms, or certainly to start the recovery on the arms to bring the lactate concentration down before you start doing recovery back on the legs. Because again, it's about the proportion of the muscle mass that was engaged, and if those fibres were inactive, or majority were inactive, they have a greater propensity for taking up the lactate that's being released and converting it back into glucose and the pyruvate. And again from Bruce Gladden, again just reinforcing the point so this becomes just convention. This is net lactate uptake at different exercise intensities, and what you can see is that they've infused, they've infused canine muscle with a fixed lactate concentration of about 9 millimoles. But this really comes back to that point that we were suggesting earlier on, that the lactate concentration they've infused the cell with is the same, but notice that what they've done is they've stimulated the muscle, and it tells us how fundamentally important raising the metabolic rate is in terms of lactate uptake. That the amount that is taken up at rest is far, far less than even under active conditions, and the VO2 is really high. Don't forget it's in the dog, so 128 mils per kilogram per minute compared to 11 at rest. So metabolic rate is far, far higher. Lactate production release is far, far higher, but the lactate concentration they were infused with is the same. So it tells us so much about the fact that we have to have a raised metabolic rate to trigger the mechanisms that are going to be required to take up the lactate from the circulation and convert it back into the pyruvate and the glucose and the glycogen.